this is actually not really a talk. This is more of a story. But before we get into that, let's start off with an exercise. So I don't know if you would stand up, if the camera would be blocked. So let's not stand up, but just everyone raise their hand. Everyone raise their hand. Come on, don't be shy. Okay, cool. If you do anything with blue teaming, if you are a blue teamer in any shape, then you can just drop your hand. Okay, cool. Anyone that is leading red teams, like really taking the lead, can drop their hand. Okay. Anyone that does purple teaming, drop their hand because you're in the wrong track. You have to go downstairs. Okay. Cool. We still have quite a few hands left. Who started their careers, like the pen testing careers, with the Metasploit framework? Drop their hands. Okay. Who's currently still using Meterpreter as a C2? Drop your hands. Who's, yeah, kind of, if it's kind of, you can drop your hands. All right, cool. Yeah, you can all drop your hands. Thank you. All right, let's talk about what I'm going to be telling. As I said, it's not really a talk, it's more of a story. We're going to meet someone called Jimmy, and Jimmy is kind of new to pen testing and to red teaming. And Jimmy was interested in it and just started browsing YouTube, looking for tutorials on how to compromise targets. So we're going to talk about that today. And Jimmy is going to face some problems. He's going to find out that endpoint protection can be a little bit of a pain. He's going to learn about staged versus stageless payloads, that the language of a potential shellcode runner could matter as well. We're going to talk about on-disk versus in-memory, and then some lessons learned. So this is Jimmy the Skid Johnson. And Jimmy the Skid Johnson saw online that Meterpreter is pretty cool. So Jimmy found a tutorial on the YouTubes on how he can generate a Meterpreter payload with MSF Venom. So Jimmy was very interested and just copy-pasted what he saw on the video. So MSF Venom, create a reverse TCP, argument L host, L port, and then as a format, he took executable. He piped it out to sigshellbro.exe. He thought, okay, this is pretty cool. I can now just email this to my target. They're going to open it, double click it because they're stupid, and we're going to be able to compromise their workstation. However, he tried to fish, so he tried to actually do that, and he got an email back saying, hey, Jimmy, I can't open this. I get an alert that something malicious is going on. So Jimmy is kind of confused because he thought, okay, this worked on the YouTube video. Why is this not working for me? And Jimmy figured out through some Googling that there's actually a website called VirusTotal. And he decided to upload this binary because apparently this website will show you if your binary is indeed malicious or not. So off the shelf, MSF Venom Meterpreter as a binary format uploaded to VirusTotal grants you 52 out of 72 detections. So off the shelf, without changing anything, there's only 52 out of 72. I was expecting everyone to just hit this, but apparently not. Apparently only 52 of the AVs that are using VirusTotal are recognizing this. So, okay, Jimmy was like, damn it, this doesn't work. I will Google further. And he found a how-to wiki article on how to hack his ex's girlfriend. Right. And he figured out through reading that article that there is something called Fireless malware. Fireless malware, pretty cool. After some research, he found out that there are actually multiple ways of designing Fireless malware, such as, for example, using a PowerShell download cradle, or it could also be a VBA document that you just send and it's going to download a payload and run it in memory. So again, Jimmy Googled and figured out that MSF Venom can actually spit out PowerShell as well. So instead of using a binary, he does exactly the same thing, but instead of using the f.exe, he now does the f.bsh for PowerShell. And now Jimmy learned his lesson. He was like, okay, I'm not just going to send this now to my target and be like, run this script. I'm first going to check on VirusTotal if this is malicious or not. So on VirusTotal, he uploads this PowerShell script, which is still off the shelf. We haven't touched anything, 27 detections. So that's already significantly less than the binary. Right, so Jimmy saw, okay, 27, not too bad, but I could probably still get detected. So what can I do? Well, upon, again, doing some more research, he figured out that MSF Venom actually has this functionality that allows them to encrypt and sometimes even encode his malware shellcode. He doesn't know that it's shellcode yet, but he knows that he can encrypt or do shenanigans with it. So he tries to do it, and he uses a PowerShell encoder x64 Zuto Dekiru. But to his surprise, that didn't change anything. Still 27 detections. Interesting. So Jimmy is now a bit frustrated because like, this is taking too long. I kind of want to just hack things, right? I just want to compromise stuff. So what Jimmy did was he opened the PowerShell script and he saw that there was like a giant blob of numbers, right? Because Jimmy doesn't know anything about hacking. He's just opening the script. He's like, oh, okay, this looks ugly. I'll just throw that away. And he uploads the script back. Now, without what we know is, of course, shellcode. He uploads it back on VirusTotal, and we see that the detection rate has dropped to 13. But it's still on 13, right? Even though the weaponization is gone because the shellcode that is going to do the connect back to the listener is not in that script anymore. Right. So Jimmy found out, again, through doing some research, that there is a thing called static detections. And it doesn't really matter if your code is malicious or not, if that specific line of code is triggering a regular expression, basically, it's a bit more than that, but basically, essentially, very high level, it's regular expressions. If your code hits one of the regular expressions, it will just be flagged as malicious. Jimmy also found out that apparently generated artifacts get signatured out of the box. So he knows now that if he just runs MSF Venom, chances are pretty significant that just out of the box without changing anything, without modifying anything, it's going to get detected. And that kind of makes sense because he deleted the shellcode and there was still 13 or 11 detections. Now, Jimmy found out that if he doesn't drop anything to disk, so again, with the Fireless malware, if he doesn't drop anything to disk, he could potentially bypass this, especially in the case of PowerShell. So instead of just trying to send it to someone, like the entire PowerShell script, send that to someone, have it that person execute it, he created a new PowerShell script that is just a download cradle, right? So the IAX, right? IRM, use basic parsing, and then just pointing it to the PowerShell script. Unfortunately, still he gets a warning. This time it says, malicious content has been blocked by your antivirus software. So Jimmy, now very frustrated, is like, why is this not working? So again, PowerShell, he tried to Google it. And Jimmy Googled the error when testing his lead exploit and found out that this is actually a protection in PowerShell called AMSI. And Dave Kennedy kind of explained AMSI, probably some other people here, because I haven't seen it. I was emceeing downstairs, so I don't know what has been said here and what it wasn't. But I guess you're all familiar with AMSI at one shape or form. So you know that actually AMSI can quite easily be bypassed. And Jimmy found plenty of Amsi bypasses online and decided to test it out. So he opens the PowerShell prompt and he just types in Amsi scan buffer, right? Amsi scan buffer in itself is just a string. That string obviously isn't doing anything malicious by itself, yet still Amsi complains. Now, you can, in PowerShell, essentially use CSharp PowerShell code and then just use the add type keyword in PowerShell to just essentially have PowerShell dynamically compile your CSharp and execute it. That way, he figured out in CSharp by using Rostamause's bypass on GitHub that you can indeed bypass AMSI. And using this bypass, he actually gets to connect back. So pretty cool. Jimmy fooled classic antivirus products, but this will probably not be sufficient for more advanced, quote unquote, anti-malware software like EDRs. So now Jimmy learned that even though there are static signatures and he can now bypass them by just not touching disk, probably with more advanced capabilities, defensive capabilities like endpoints detection and response, EDRs, they will probably have something like called dynamic analysis, which might still detect that AMSI bypass, or even if that doesn't get detected, probably the callback to the handler for interpreter will probably get caught. So he also realizes that this last thing, like the dynamic analysis, is probably a bit harder to deal with. Right. So now Jimmy finds himself in a bit of a situation because Jimmy now knows, okay, if I use off-the-shelf payloads, I'm going to get detected. If I don't touch disk, but use things like PowerShell, I might still get detected because of that dynamic analysis. So Jimmy wanted to figure out a way to maximize the control that he has over his payload. And he figured out that in order to have the most chance of success to bypass defenses, he probably would have to create his own custom loader or even custom C2. Now, Jimmy learned that there is actually a thing called Shellcode, which allows you to create your own loader or wrapper around that shellcode and then execute it within itself or potentially inject it into another process. Once again, he found a tutorial on YouTube on how to generate interpreter shellcode, but he knows that this is probably going to get signatures. But are there ways to potentially modify shellcodes to evade detection or break detection? Well, yes, there is. This is a screenshot taken from an excellent, really excellent blog post from Huntress, which is also the company that John Hammond works at. So probably all familiar, or most of you are familiar with John. And in this blog post, they explain that a lot of malware essentially uses a technique called API hashing. Now, the reason why they do that is because if they don't use API hashing and reverse engineers or like getting wind of the payload and extract it and do some reverse engineering to it, they will just very easily see the API calls that are being made by the malware. So in order to try and quote unquote obfuscate it, in my opinion, API hashing has a very obvious like indicator of compromise in the sense that this random hexadecimal is going to get pushed. But at least this is better because there's some sort of obfuscation in the sense that you don't immediately know what API call is being called. So there's a thing called API hashing, which essentially takes the string formats of your API call, for example, virtual alloc, and is going to just classically, a classic hashing algorithm would be ROR13, so bit shifting all the bytes 13 places. And that essentially gives you a hexadecimal representation of what used to be a string value. In this case, win inet, for example. Now, as I said, classically, a classic hashing algorithm is ROR13, which means that a lot of out-of-the-box shellcode generators are going to use this algorithm in their payload generators. Before anyone asks, yes, Cobalt Strike does this as well. Metasploit does this as well. So ROR13 is definitely something that is out there. EDR vendors and just SOC analysts in general figured that out, that a lot of malware uses ROR13. So essentially, ROR13 kind of static, right? It's not doing anything dynamic. It's just bit shifting. So if you know the value once, you're going to know it again the second time because the API calls always have the same name. For example, get proc address, virtual alloc, always have the same name. So the ROR13 value of these API calls will always be the same. So you could write signatures for that, obviously. And that is what happens with, for example, Metasploit, but also for Cobalt Strike. So Jara rules have been created that essentially just look for ROR13 equivalents of specific API calls. Now, in this blog post of Huntress, what they have done is essentially the first step was breaking the shellcode. So you're going to see that this, for example, 7267774C is now just replaced by 11111111. And if you would look at VirusTotal, the shellcode in its raw form with the ROR13 has 17 detections. Now, the broken down form, obviously it's not going to work anymore because we just replace it with once, but just to see that the static signaturing is brittle, we got it down to 2 detections. So essentially, if we change ROR13 to another arbitrary value, we might evade some static signaturing. Right, so now Jimmy knows that modifying shellcode could potentially help evade detection. However, reading and more importantly, modifying shellcode is not really a very easy task, right? Unless, of course, you use public encoders, for example, Shikata-Ganai, which is one that is very famous. If you use that, that's going to work. It's going to encode your shellcode, but of course, it's public. So once again, public encoders are going to get signatured. So Jimmy decides to, even though he now has the knowledge to encode shellcode, he's going to go another route and go for lower hanging fruit first. So now Jimmy has several design decisions to make, right? Staged versus stageless payloads, the language of the runner. What technique are we going to use? Are we going to drop on disk or are we going to stay in memory? Right. So before we start with answering all those questions, we first have to understand staged versus stageless. So staged payload is typically a small code stub, which is going to fetch a bigger code stub quite easily. It's easier to embed, right? Because it's smaller in size. So it's easier to embed in potential loaders or even inject into other programs as the size is smaller. However, most of the tools, frameworks like Metasploit or other C2 frameworks that allow for staging are very, very, very Opsec unsafe, as we're going to see in just a minute. Staged payloads are very, very dumb, which means that they can get pulled by automated tools like sandboxes. Staged payloads usually sit on the same server as the actual C2 itself as well, especially red team operators that don't really know what they're doing are typically going to use the same server for staging as the actual C2. So if your stager eventually gets burned, your entire C2 infrastructure will get burned. And you typically, if you're using open source frameworks or even pay tools, so not your own shellcode or stagers, you don't really have any control over how this connection works, how they are going to call back, how they're going to pull that data and then execute it. So typically, sometimes even these staged payloads reach out over clear text, and we're going to see that in a bit. This is an example of what happens if you leave Cobalt Strike, if you leave your team server online, exposed to the entire internet, with staging turned on. So eventually, after a few hours, or if you're lucky, a few days, you're really lucky, a few weeks, you're going to open up your team server, your clients, connect to it, and suddenly be very happy. You're like, oh my God, this is amazing. I have so many callbacks. Until you start realizing that these are not your targets. These are all sandboxes, automated sandboxes, just scouring the internet, trying to pull random stagers in order to do incident response or just threat intelligence in general. Right. This is what happens if you turn on staging. So if you create a staged payload for Metasploit from Interpreter, you're actually going to start a multi-handler, which is just going to be a web server. And if you would browse to that web server manually, so not using the shellcode stub, you're actually just going to see that your TCP handler is receiving a connection. So it's going to try and send that stage for you. There's no symmetric key exchange or anything like that. It's just open to the public. And you can see, well, maybe not because resolution, etc. But the first two number or letters are MZ, which is kind of the magic byte value for a PE. So it's just a binary just sitting in its totality, right? In plain text, basically, just waiting to get pulled by whoever, right? There's no authentication or authorization going on. Anyone can just pull this stager for you. Now, if Jimmy decides to go for this staged approach, he doesn't only run into the problem that his stager is basically dumb, but he also runs into a double problem with potential web proxies, right? So typically in C2 scenarios, so most of the time those are red team scenarios, you have to deal with web proxies. Because if your organization, your target organization is using some kind of proxy service like Blue Code, and you're trying to serve to a website that isn't recognized by Blue Code, or even worse, categorized as phishing or whatever, as malicious, you're going to get this very nice pop-up. In this case, it's for FortiGuards proxies. And it's basically going to say, hey, this web page is blocked. Something doesn't feel right. We're not going to allow you to browse to this website. Now, if you're using staged payloads, you actually run into this problem twice. Because the first time, it's to actually reach the stager. The second time is for your C2 channel. So you now have two things to worry about. If you're using the same server, which I don't recommend, but happens, then you only have to deal with it once. But of course, if you're separating command and control, so you have a staging server and your actual C2 server, you have to do this twice. So you have to categorize your stager and your C2 traffic to try and bypass that proxy validation. And then we have another problem, this time with stageless shellcode. So imagine, okay, Jimmy finds out that staged isn't the way to go. He wants to go stageless. Well, we have a problem, especially when we're compiling or trying to code our malware in C, because typically a stageless payload is magnitudes bigger than your staged payload. Makes sense. If you have a blob, a binary blob of 2,000 characters, and you try to compile it in C, you're going to have a bad time because it's going to have to compile for quite a bit of time. So is there another way around that? Yes, there is. You can change your language, for example. In C#, which is a much higher level language than C, it doesn't have to deal with that long compiling thing. So if you have a 2,000 character stageless payload, the compiler is still going to be relatively fast in compiling your payload. The problem is, though, if you're using higher level languages, typically those are much easier to get reverse engineered. We're going to see an example at the end of this presentation, but essentially C# can basically just be reversed in clear text. So you open the binary with the nspy, for example, and you're just going to see the code as it was written. There's no kind of obfuscation or anything like that. So you have to keep that into account. There's also more scrutiny. The higher level language you program in, the more scrutinized you're going to get. For example, anything that is using the CLR, which is VBA, which is PowerShell, which is C#, has to deal with AMSI. Of course, we have seen that we can bypass AMSI, but nevertheless, it's still a security control that you have to take into account. Then another thing is portability, right? If you're programming in a language that isn't able to get interpreted by the endpoints, then your payload is never going to run. For example, if you are coding in Python and the endpoint doesn't have a Python interpreter, your payload is not going to run unless you package it to an executable, but that's another story. And then size, some languages will bloat your payloads. For example, Golang. I love Go because it has kind of evasion out of the box in the sense that it's not easy to reverse engineer, but it's going to increase your payload by quite a bit. And then, of course, the final part, which for me as a developer now for Cobalt Strike, but as a red teamer as well, is of the most important, and that is control. The lower level your language is, the more control you have over what happens, right? Memory allocation, freeing up memory, zeroing out memory, garbage collection, stuff like that. You have full control, which is also much more dangerous because it's more error prone. If you don't know what you're doing and you're creating memory leaks, you could have a bad time. You could end up crashing the system because it doesn't have any more resources to give you. And then we have the technique of the runner, okay? So with shellcode is kind of special in the sense that it's capable of running on its own. So we have different avenues to explore. We could stay in our own process, right? So we could just create a thread or even be threadless in ourselves. So create a pointer to our shellcode and use that, which is nice. But of course, your payload is going to stand out because it's probably something that has never been downloaded before on an endpoint and is going to create an internet connection, which again, dynamic analysis might be, what is this? So we have another avenue, which is process injection, right? And for process injection, we have, again, a lot of options. Do we do a very classic create remote thread process injection? Do we use SKU user APCs? Do we use process hollowing, process herpaderping? Yes, that is a real thing. Thread hijacking. Yeah, so there's a lot of things that we could potentially do. Then on disk or in memory, again, Opsec to consider. If you drop on disk, you create an artifact, which could then, of course, be inspected, which is easier to be collected as well by incident response than in memory, because in memory, it only lives in memory, right? So if the server reboots, that memory is basically lost. So they would have to do live forensics on that system. But most persistent techniques will require some form of artifact anyway. So If you ask me as a red teamer, I would go with on disk, but I would go with decoupled on disk. So I would not get instant execution. I would be very strategic. For example, do a COM hijack or a DLL hijack, drop it somewhere that gets loaded by default by a program that already has internet connection, Teams or Slack. Yeah, and essentially that will help you because you already are in a trusted process that has internet connection, which doesn't necessarily stand out immediately. So a very, very quick walkthrough, okay? So a red team worthy payload. Step one, staged or stageless? In my opinion, neither. Well, kind of. The best way to go, if you ask me personally, would be to have a custom quote unquote staged payload. It would essentially be a stageless payload, which you are going to stage. Kind of weird, but that's how it goes. So essentially what you do is you create either stageless shellcodes or an executable, and you create your own, so not off the shelf, not some random stager that you find on the internet. You create your own low-level stager. Typically what I say when I say low-level, I mean C, or if you're smart enough, assembly. Right, so design choices. If you're going that route, what can you do? Well, there are three actually, but primarily two DLLs, so libraries that you can use in C for internet connection. So you got WinINet or WinHTTP. You can use either are fine. I don't prefer the one over the other. I like them both, so you have that option. And then what can we do to actually stage our payload? Because as I said, essentially staged payloads are dumb, but you can take specific actions to be smart. You could have IP filtering. You could do execution guardrails. My favorite, which still works, it used to even be more stealthy, but now that domain fronting doesn't exist anymore, kinda. You could still use CDNs like Azure or AWS CDNs, which half the internet is built upon these days. So it's not really going to get immediately blocked by a proxy. And you could specifically state certain rules. For example, hey, if I get in requests to my CDN endpoints with a specific header, like an E tag, for example, that has a specific value, then I want you to serve this page, which would be our payload. If I get anything else, please redirect to some other random page. So that now means that because we are creating our own custom stager, we can keep that into account. We can inject that header into our requests. So a randomly generated header with a random E tag value, and we could use that as a key to get to our actual payload. That means that if someone else or something else, an automated tool, tries to fetch the payload without that header, it's going to get redirected to a more innocent page. Also helps you with protection against potential snoopers or robots, crawlers. And then another thing we can do is encrypt our shellcode. Do we encrypt it? Do we do RC4 encryption? Do we do AES encryption? Do we encode it? Do we do base64 encoding? Do we do both? Those are all things that you can now do because you are going to create your own stager so you can build that decoding logic or decrypting logic inside of your stager. And then the language. That's another common question that I get, the language. What language should I code in? Honestly, there's really no best answer here. If you ask me personally, I like my runners in C and C++. And I know that some people of Inviso are watching and are in the audience, so they know, because that's what I used to do. I used to write malware for Inviso, and I always used, well, in case of droppers, C or C++. But any language works fine. Just remember the scrutiny, the increase of payloads, et cetera, et cetera. But for example, MIM, which is now a popular language, can also compile to native C and already has dynamic imports by default. So you already have a little bit of obfuscation in the sense that your API calls are not immediately going to be in the import address table of your payload. That's kind of cool. And it, of course, depends on your coding skill, right? If you are not proficient with C, it's going to take you a long time. Higher level languages are going to be better for you if you're new to coding, and the more experience you get with those higher level languages, the faster that you then essentially could level up your game and use lower level language. And then finally, technique. There's no best answer here. Again, it's kind of flavor of the month. Just keep an eye on Twitter or Mastodon now, I guess. For the flavor of the month, right? People share their TTP, so that's kind of nice, both for red and blue. Unfortunately for blue, red is usually faster at implementing these new flavor of the month techniques than your EDR or your endpoint security is in signaturing them. However, it's still a cat and mouse game as always. Indirect syscalls or syscalls in general are still currently the best way to go, but different EDRs trigger on different techniques. Defender for endpoints will trigger on other things than CrowdStrike would, and vice versa. Also depends on the delivery method. Some things are considered more malicious than other things, as I already mentioned. My favorite thing to do would be COM hijacking or DLL hijacking, as that automatically gives you that trusted process with internet connection, which gives you a bit more freedom and breathing room for your operations. And then on disk or on memory, again, depends on what your objective is. You probably don't want to persist on every single workstation or server during your operations, but you'll probably want to persist on some of them. So ideally, you have a mix. You have a mix of lateral movement in memory and persistence on disk. That way, you also split up your IOCs. So when you get detected once, not your entire operation gets burned because you're using different things on different machines. Additional tips for dropping to disk. It sounds very obvious, but I've seen people make so many mistakes. First of all, clone your metadata, people. Like if you compile your payloads, for example, with Visual Studio, you're going to get metadata like on the left here, which is like no real developer has this. This makes no sense. When incident response sees something like that, they could immediately see that this is potentially like malware, or it already stands out. You can just clone metadata of a trusted DLL, for example, Amsi, just clone it over, call your payload Amsi original.dll or something like that, whatever, make it blend in more. Then finally, strip your debug symbols. And the reason why I put this one in caps and underlined is because for a while, I made that mistake. I did some red team ops and I didn't strip my debug symbols because I didn't know that that was a thing, honestly, when I was starting out my red teams. Until we actually had instant response from Inviso themselves, because Inviso doesn't only do red teaming, they also do instant response. And I got a message on Teams that was like, hey, Jean. I'm like, yeah, what's up? Could it be that you have done red teams for this, and this client? I was like, yes. How do you know? Like, yeah, we found a payload that you generated and we just put it up on VirusTotal. We saw in the PDB, which is the debug symbols, your name. And we just used your name on VirusTotal and we found all these other payloads that were also in VirusTotal, which were incriminating like customer names. I was like, oh, damn, is that a thing? So yeah, stripping debug symbols, it sounds very trivial, but people tend to forget, especially newer operators. Another thing you can do, but be careful with that because sometimes that in itself also stands out, is time stomping. What it essentially means is you're going to change the time created date to something older. So if you drop it on disk, it's going to not look like it's just dropped there now. It's going to look like it was there for a few months or even a few years, depending on your target. And then knowing your tools. And this is so obvious once again, but unfortunately, not a lot of red team operators actually have seen the other side of things. So I can guarantee that some of you who are now doing red team operations have never been to a SOC before, have never seen incident response being performed live. And sometimes you'd be surprised with what endpoints actually detect or what logging capabilities are possible on endpoints. This is very, very basic. This is Sysmon that is running with a very normal configuration like Swift on securities, Sysmon configuration, which is kind of the de facto standards. If you just want like one configuration and you don't want to tweak it, people always go to Swift on security. And Sysmon event ID 8 exists, which is create remote thread. And that essentially says, hey, whenever a program creates a remote thread legitimately, that's the API call name, create remote thread. Whenever that happens, please fire off this event ID, and that's going to happen. So they will see that a create remote thread has happened. They will see the parent image and the target image, so they will see where it originated from. And why this one in specifically I wanted to call out is because in normal times, not a lot of processes do this. Like in normal operations, legitimate processes don't really do code injection that much. So you'll probably stand out when you do that. Of course, this can be bypassed. You could queue a user APC, for example, which would not create this event ID 8 rule or trigger. But again, knowing your tools, very important. Then this was what I meant when I was talking about C# and compiling C# to actually drop on disk. If you get detected, people could just fetch that payload, open up the NSpy, and they will just see your code as is. There's no obfuscation there. They don't have to do any heavy reverse engineering. They can just see the code as it was. This is the import address table of a specific tool or DLL. And essentially what I wanted to show you here is that your API calls, if you're not doing indirect API calls, like that function hashing that I talked about, they're going to show up here. So in this example, we have this random DLL, sec699, which is a DLL that we use in sec699, kind of obvious. And you can see that there's a function in there called winExec. So that means that we're using the winExec function in that DLL. And winExec is not something that is used anymore. It's a very old and deprecated function that essentially spawns a new process. So when you see that as an incident responder, it's not something that a lot of DLLs use nowadays. Yeah, same thing here. We have an exported function called runme, probably a function name that is not used in legitimate purposes. And here is what you get when you take these hot pro tips, right, into account. So this was a tweet that was tweeted not that long ago, October 31st of this year. And essentially this individual was able to run Mimikatz today on a default config Defender for Endpoint protected host. So not even just regular Defender, we're talking about Defender for Endpoint here. And he just used a custom stager, which was created by Hashergrat or Hashergrat, yeah, I don't know how to say that name. She's quite famous in both red team and blue team. She created PE Bear as well, if I recall correctly. And she recently released a library that is able to do custom stagers. So essentially, Mimikatz off the shelf, no encoding, no encryption on a Defender for Endpoint protected host. And it just simply worked. So with that said, that was the end of my presentation. Hopefully you liked this story about Jimmy the Skid. And if you have any questions, feel free to ask them now.